everybody, and welcome to your video on continuing Taylor's series. This is really picking up after you've done the Desmos, and remember that worksheet goes with the Desmos to help you practice. Ideally, what we would have done after the Desmos is kind of wrap things up here, specifically about sine and cosine and talking about the different summation notations, and also building one more series. We obviously didn't get to that, so let's do that right now. We're going to talk a little bit about error today, and that's going to set us up well for next week. We're in the middle of Unit 10 right now. We are skipping more convergence. We're doing Taylor's series. Then we'll go back to convergence. All right, so the Desmos first built up sine of x, and you did that with some trial and error, with some sliders, and eventually you got to this. Now, I'd like you to write this down because we're going to put some summation with it and make it formatted well. Now, I know you might be thinking, I just wrote this down, but people, you have to memorize this, and writing it over and over again, the repetition is what's going to build the fluency and the memorization, okay? So that was sine of x. That was cool. Hopefully what we talked about in class is the fact that sine is symmetric to the origin, and functions that are symmetric to the origin are odd. Sine is an odd function, hence the odd powers that it has, and odd factorials. Cosine is an even function because cosine is symmetric to the y-axis. Anything symmetric to the y-axis is even, and even functions... and cosine has all even exponents. So on the Desmos, we didn't have to build cosine from scratch with like sliders and discovering it. We just differentiated sine. So to go from sine to cosine, we do the derivative. So I want to show you something cool with factorials here. All right, I'm going to do the derivative of this. X cubed would be 3x squared. The coefficient of 1 over 3 factorial goes along for the ride. And then I have 5x to the 4th over 5 factorial minus x to the 7th over 7 factorial plus ... I'm going to erase this just because I'm going to need some space here, okay? All right, let's talk about this because I really don't feel like reducing, like doing 5 factorial or 7 factorial. There's a quicker way to reduce this, right? We're not just going to leave it like that. We're going to clean it up. So let's think about what is 3 factorial again. 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. There's 7 factorial. All right, so watch carefully. You ready? I have 3 over 3 times 2 times 1. Well, let's cancel the 3's. I have 5 over 5 times 4 times 3 times 2 times 1. I'm going to cancel the 5's. Oh, what the heck did I write here? Hold up. Okay, there we go. 7x to the 6th. There we go. So now I'm looking at this. I have a 7 here and a 7. And what is left? If I have 2 times 1 left, I can write it as 2 factorial. 4 times 3 times 2 times 1. Well, that's just 4 factorial, isn't it? And 6 times 5 times... All right, I'm not re-recording this, so we're just going to go with the errors. I'm fixing it as I go. 6 times 5 times 4 times 3 times 2 times 1 is 6 factorial. So let's go ahead and clean up cosine here and write it a little bit nicer. So I know that cosine is 1 minus, what's left up here? X squared over 2 factorial. Plus, then I have x to the 4th over 4 factorial. Then I have minus x to the 6th over 6 factorial. Plus, ... Because these are infinite series, they go on forever. So you need that plus ... Okay. So what I want to do is talk about the summation notation. In Desmos, it did give you summation notation, and I believe it was assuming that the series started at 1. You can write it like that. My personal preference is to write it starting at 0. It's just how I learned it, and I don't know, it's easier for me to remember it. You can remember it either way, but I just want to show you, can you write down the way to do it starting at 0 as well? So then you have both. I just feel like the patterns are a little bit easier to see whenever you start at 0 than starting at 1. Again, it's personal preference here. So the sine series is this infinite series. It is equal to the summation of all the terms from, now this again, starting at 0, this method. If it's sine, I would have, let's try this one, -1 to the n, and then I have x to the 2n plus 1 all over 2n plus 1 factorial. Okay, it's always a good idea to test it and make sure this makes sense. If I plug in n equals 0, That'd be negative 1 to the 0, which is 1, so positive. And then I have x to the 0 plus 1, which is x, all over 1 factorial. And 1 factorial, don't forget, 1 factorial is 1, and 0 factorial is also 1. 1 factorial, that's kind of obvious, but 0 factorial is 1. That's something we're going to come across here. Sometimes that throws people off. All right, so this seems to work, negative 1 to the n. And then let's go ahead and do cosine as well. I should probably get rid of that scribble here if I can. All right, jot that down for yourself. Okay, cosine. I'm going to do another summation, and I'm, again, going to write the way starting at 0. So if I have n1, the first term, or when n equals 1, my power is 2. When n equals 2, my power is 4. When n equals 3, my power is 6, and the factorial matches. So we have a doubling connection going on here. Always look for patterns like that. So let's try out if this sign changer will work, negative 1 to the n. So whatever I have here, I multiply by 2, and the denominator is the same. All right, let's test it. Let's try plugging in 0. Negative 1 to the 0 power is 1, positive, I want that. X to the 0, anything to the 0 power is 1. 0 factorial, like I said above, is 1. So I'd end up with just 1, which is my first term. All right, cool. So in class, we also didn't get to build our third big series, okay? So there's going to be, I call them the big four. First one is sine, second one is cosine, and you need to have those series memorized. Luckily, we're going to use them so much, you're kind of just going to memorize it naturally because we'll be working with it a lot. Let's build our third big four series, and this one's kind of cool. We're not going to go in Desmos with the sliders with this one either. We're just going to go ahead and build it from scratch. And it's kind of cool. It's going to use long division, which you did in Algebra 2 and which you reviewed this year whenever we did integration by long division. Okay, so first is sine, next is cosine. The third one is a rational function. Rational functions have an x in the denominator, and it is 1 over 1 minus x. So we want to write a polynomial for this rational function. This is very much not a polynomial because polynomials cannot have a variable in the denominator. But we're going to go ahead and find a polynomial that could approximate it. So what does 1 over 1 minus x mean? Well, it means you're going to take 1 and you're going to divide it by 1 minus x. Now, this might seem a little bit weird to do, but we actually can divide this out. So let's just do the long division and see what happens. What do I multiply 1 by in order to get 1? Well, I multiply by 1. Then I distribute the 1 across. So then 1 times 1 is 1. Minus 1 times x is negative x. Now I'm going to subtract. Okay, 1 minus 1 cancels. Nothing minus negative x is x. Next, what do I multiply 1 by to get x? I multiply it by x. Now let's distribute the x. X times 1 is x. X times negative x is negative x squared. Let's subtract. X minus x cancels. Nothing minus negative x squared is x squared. Let's do it again. Okay, what do I multiply 1 by to get x squared? I multiply it by x squared. So then multiply across. X squared times 1 is x squared minus x cubed. Subtract, those cancel. Nothing minus that is just an x cubed. I'm going to do one more out, but I'm thinking you probably see the pattern here. What do I multiply 1 by to get x cubed? And that would be x cubed. Okay, then you multiply that across. So then x cubed minus x to the 4th. Subtract, and you get x to the 4th. If you want to see what do you multiply 1 by to get x to the 4th, it is x to the 4th. But check it out. This just keeps going. This is a very obvious pattern here. That is a polynomial because you just have powers of x here. So therefore, I can write this rational function as 1 plus x squared plus x cubed plus x to the 4th plus dot, dot, dot. We get the point. All right, so we should also write it in summation notation because you need to know the generator for each of the big series. And remember, the generator is like your a sub n term that goes right here. So this one isn't too bad to write. I'm going to start when n is 0 and go to infinity because I personally think it's easier to see the rule or the pattern when you start at 0. So this is the 0th term, the first term, the second term, the third term, the fourth term. You should notice you always have a power of x, and whatever term you're on, that's the power of x. Technically, this 1 is an x to the 0 because x to the 0 is 1. All right, so I should be able to write this as x to the n. And I think this is the easiest one to remember out of the big four because there's really not much to it. It's just powers of x. Cool. Just as a little sneak peek teaser here for what's to come, the last of the big four is e to the x, and we will build that very soon, not quite yet. So I want to talk a little bit about error and what error really means here. So let's go ahead and, there we go. Let's think about error. Okay, so why are we even doing Taylor series again? Let's make sure we remember. The main goal of a Taylor series is to approximate values of functions. So this is something we're going to really make a big deal out of more and more as we do this. But I think we had briefly talked about in the beginning of the Desmos, why did we have Taylor series? It's because we couldn't do things like cosine of, I forget what the first slide of the Desmos was. Was it 0.01 or something? How did mathematicians do that? They used a Taylor series. And also just a reminder, the way your calculator finds things like cosine of 0.01, calculators are programmed with Taylor series, so they're accurate to 9 or 10 decimal places. So your calculator finds this stuff with Taylor series as well. Okay, so you're going to be doing a lot of approximations with your Taylor series, and just to show you something kind of cool, if I take my polynomial for sine, which was 1 minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x, if I stopped at the 7th degree, and let's say I wanted to estimate what is sine of 0.5. Well, 0.5, half a radian, that's not a unit circle one you have memorized. The true value, the exact value, is this, okay? The approximated value using the 7th degree Taylor polynomial is this. And look how close those are. Those are close. Wow, all the way to here. That's really accurate. And that was only with 1, 2, 3, 4 terms going to the 7th power. That's pretty cool. So that is why we use Taylor series, to estimate non-friendly functions like sine. Unless it's a unit circle value, it's not very friendly to evaluate, okay? So another thing I want to point out, we already have estimated function values using linearization, and that's just a fancy word again for tangent line approximations. So we've already been doing this. And another thing that we're going to talk a lot about is how a Taylor series is just a tangent line. So a tangent line is just a first degree Taylor polynomial. So that means if you took your polynomial and you only went out to the first power, not like the 7th, the 5th, or the 3rd power. So you've kind of been doing Taylor series this whole year with a tangent line. So a tangent line is a first degree or linear Taylor series. It's just tangent lines aren't as accurate because we usually go farther than just the first degree. Because the further out you go, if you kept going to x to the 9th or something, it would get even more accurate. Also, I want to point out something on the scoring guidelines. I'm sure you've noticed that whenever you look at the scoring guidelines, whenever we write our tangent lines, I usually tell you leave it you can leave it in this form, which is point slope. But if you look at almost every scoring guideline, they're always going to swing this constant over and write it as y equals something. And that's to make it look like a Taylor series. This is a first degree Taylor series because it's to the first power. And we're going to be adding on more powers, to the 2nd or to the 3rd. But as we practice this more, this will be even clearer to you. But just to point out why they write it like this, is because it technically is a Taylor series, and this makes it look more like a Taylor series. All right, so let's continue with our 1 over 1 minus x. So I have f of x equals 1 over 1 minus x. Oh, one other thing. On your calculator, we're going to be doing this a lot. To get factorial, which I did up here, in order to get the factorial, you hit the math button go over to probability, and go down. That's your factorial. Okay? So, anyway. All right, 1 over 1 minus x. We already established that it was 1 plus x squared plus x cubed plus dot, dot, dot. Keeps going. Let's talk about how we're going to make approximations, and let's also talk about some notation here. Okay, so first of all, what we want to do is let's approximate. So jot this down with me here. We're going to do one example, and then we'll call it quits here. Let's approximate f of 1/2 using the cubic polynomial approximation. Oh, man. Come on. Okay, the cubic polynomial approximation. I can't fit that on the line. All right. So what that means is I'm going to take this, and I'm only going to go out to the cubic term. I'm not going to add infinitely many, obviously. Like, I can't actually go out to infinity. So I'm going to chop it right here, and I'm going to call it P for polynomial of x, and I'm going to call it 1 plus x squared plus x cubed. Now, if I go out to the third power, I call it P sub 3. So whatever subscript you put on P of x, that is your degree of the polynomial. Now, another thing is whenever you have an infinite Taylor series and you chop it somewhere, you are truncating it. Okay? Like, you can truncate words, like probably is probs, maybe is mabes, totally is totes. You know, the list goes on. But you can truncate a polynomial as well. That just means you chop it and you end it. So P sub 3 is equal to this. Now, I can't put the dot, dot, dot after because that's not technically right, because the third degree Taylor polynomial doesn't keep going. It stops at that. Okay? So we're going to call this our truncated, and we're going to use the word truncated kind of a lot, and it just means a shortened polynomial. So that is my truncated polynomial, and what we're going to do is we want to approximate a specific value, and what's the specific value? We want to approximate 1/2. Okay, so what we're going to use is this to approximate 1/2. So P sub 3 of 1/2 is equal to, now let's use some good notation here, the function value of 1/2. Remember, your function value is f of x. So our function value is approximately equal. You have to be careful on your equals and approximately equals. You don't want to mix those up. Is approximately equal to our polynomial value at 1/2, and our polynomial value, P sub 3, is equal to the following: 1 plus x squared plus x cubed. And I'm going to stop there. So let's go ahead and simplify this. You can pause the video, and I want an improper fraction here. Simplify it. Oh, I just realized I have a little typo here. 1 plus x plus 1/2 squared, 1/2 cubed. Don't mind me, I'm just fixing this up. You go ahead and find yours, okay? 1 plus x plus 1/2 squared plus 1/2 cubed equals. There we go. Whoop. All right. If you go ahead and do your common denominator workout, you should get 15 over 8. That is your estimated value. Okay, I'll be right back, guys. Keep going. Sammy, do your warm-up. Oh, yeah, I'll miss you too. I'll be right back. Sorry.